Hello and welcome back to the channel. So today we are going to discuss the second practice problem on linked list, and today we are discussing lead code problem number 142, linked list cycle 2. So the question says that given the head of a linked list, return the node where the cycle begins. So if there is no cycle, return null. Now after that they have explained what does a cycle mean. So instead of reading that out, I'll probably explain it in simple terms. So cycle is nothing but when a node loops back to some previous node. So as you can see in this example, this particular node is looping back to a previous node which is 2. Again, this node loops back to a previous node. So if this kind of loop is present, then we say that a cycle is present. And if it's a normal linked list like the ones that we have been seeing till now, then we say that the loop is not present and we need to return null in this case. So in this particular case, we need to return this node which has a value 2 because the cycle actually begins at this node. So yeah, we'll return this as an answer. So again, this problem can be solved in two ways. So first by maintaining a hash set of the visited nodes, and second using the tortoise and rabbit algorithm that we discussed in our previous video. So when we use the rabbit and tortoise algorithm specifically for detecting cycles, that algorithm is also known as Floyd Cycle Detection algorithm. So let's first discuss the more obvious set-based approach. So in this approach, we simply traverse the complete linked list using a helper pointer, and we keep adding the current node to a hash set. So as we move to a new node, we check if this node is already present in the hash set or not. Now there are two possibilities. We might never find a node again and eventually the current node will become null. So this is the case where there's no loop in the list and we can return null. In other case, we will eventually reach an already existing or already visited node. So this is definitely the node where the cycle starts and we need to return the node. So for a quick example, let's say that this is our hash set and we start traversing from this particular node. So now this node does not exist into our hash set, so we'll in add it to our hash set and move to the next node. Similarly, 2 will be added, 0 will not be there, 0 will be added, then we'll go to minus 4 won't be there, so we'll add it. Then we'll come back to 2. Then we'll see that 2 is already present and we'll simply return this node because this is the node definitely where the cycle starts. In another case where there's no cycle, what will happen is that we'll add this node to hash set, we'll add this node to hash set, and we'll reach null. And if we reach null, that definitely implies that there's no cycle in this list. So what we'll do is we'll simply return null. So the time complexity for this approach is big O of n because we are doing a linear traversal of the list, and where n is the size of the list obviously, and the space complexity is also big O of n because we are using helper space in form of the hash set, and the maximum size of the hash set could be equal to the total nodes in the list. So the big O of n is the space complexity as well as the time complexity. The second approach is a bit tricky, and in my opinion, it is really tough to come up with this approach on your own during an interview. And I think it'll be really difficult to intuitively explain why this approach actually works. So for this particular approach, we'll take help of maths and we'll try to prove it mathematically that this approach actually works. So first, let's try to understand that what is the algorithm and what are the steps, and then we'll try to prove that why do these steps work. So what does this algorithm say? It is that we need to start two pointers from the first node, and one is going to be your fast, another is going to be your slow pointer. Now slow will move one step at a time and fast will move two step at a time. Now according to the algorithm, so if there is a cycle, then these two pointers will definitely meet at some point. So this is the first thing that the algorithm says. The second point is that once these pointers meet, if we start two pointers again one from the first node, second from the point of meeting. So once the two pointers meet at a point, now after this, if we start two pointers again, one starts from the first node of the linked list and the other starts from the point where they met, then the point where these two pointers meet, it is the cycle start point. So when we start these two pointers will definitely meet again, and the point at which these two pointers will again meet will actually be the start point of the cycle. And if this doesn't happen, if these two things don't happen, like the initial two pointers do not meet, so the fast pointer will definitely run into null before these two pointers meet. So if the fast pointer runs into null and these pointers haven't met yet, then definitely there's no cycle in the list. Now, one more thing to remember is that the two pointers that we are going to start in the second step, both these pointers are going to move by one step. So none of them is going to move by two steps. Now it is really difficult to understand, or it is really difficult to intuitively explain why this will happen. And I think doing a little bit of mathematics or a mathematical proof is the only way to clarify that this is actually true. So now let's try to prove it mathematically. So let's say that this is our linked list, and this is the head of our linked list. And we can obviously see that there's a cycle in this linked list, and the node where the cycle start is this particular node. Now let's define some distances. So let's say that the point where the first two nodes, the fast and slow pointer meet, is this point. So they meet at this particular point. This is the meeting point of fast and slow. Now let's define some distances. So let's say the distance between the head and the start of the loop is L1. Let's say that the length of this complete cycle is C. So in this particular case, the length of cycle is 4, but we are trying to prove it for the generic case, so we'll say that the length of the cycle is C. The distance between these two nodes is L1, which is actually 4 here. And let's say that the distance between the meeting point and the start of the cycle is L2. So this distance we are taking as L2. And also let's say that the fast and slow pointer before meeting, the fast actually moved n times in this loop. So we can say that the total distance by fast pointer, total distance by fast is actually going to be equal to L1 because it would have covered this particular distance. Then it would have covered n cycles before meeting. So if it would have covered n cycles or n loops, the total distance in that cycles would have been n into c, which is the number of cycles into the length of the loop, plus in the last cycle where it reached till L2 and then it finally met slow. So it would have also covered a distance of L2. So this is the total distance covered by fast. Now what is the total distance covered by slow? So slow meanwhile only moved from head till the point of meet. So slow moved in this path. So basically total distance covered by slow would have been simply L1 plus L2. Now we can also say that the total distance covered by fast is actually twice the distance covered by slow because fast was taking two steps at a time. So we can say that the distance covered by fast, which is L1 plus n into c plus L2, is twice the distance covered by slow pointer, and this equation reduces to n into c is equal to L1 plus L2. Now this could also be written as n into c minus L1 is equal to L2. So as you can see that for some particular value of n, for some value of n, this equation, this particular equation is going to have a positive solution. So n into c minus L1 for some value of n will give a positive value. Then we can say that there actually exists a n such that we can get a positive integer value for L2. And if we have a positive integer value for L2, so we can easily say that there will exist a meeting point for both the nodes. So by this equation and by this logic, we can actually conclude that there will be a point where these two nodes will meet if there exists a cycle in the linked list. Now we need to also prove the second part of the algorithm, that if we start one node from the starting and one node from the meeting point, then the point where these two nodes meet again is actually going to be the start of the cycle. So now this above equation nc equal to L1 plus L2, this equation can also be written as L1 is equal to n minus 1 into c plus c minus L2. Right? I have taken 1c from n into c, so I am only left with n minus 1c, and I have combined that 1c with c minus L2. Now let's try to carefully understand that what is c minus L2, which distance is c minus L2. If we see, the distance between the start of the node and the meeting point is L2, and the whole loop is of length c. So this distance from meeting point to start point, this distance is actually going to be c minus L2, right? Now our equation says that L1 is equal to n minus 1c plus c minus L2. So L1 will basically be so if we start a node from the starting of the linked list, that is from here. So L1 is actually going to be the distance covered by this particular pointer till the start of the cycle. So if we start a node which is moving one step at a time, then L1 will be the distance covered by this pointer from the start of the linked list to the start of the cycle. So this is L1. And if we start a pointer from the meeting point, if we start a pointer from here, then what will be n minus 1c in plus c minus L2. So if we start a pointer from this particular point or the point of meeting, then n minus 1c will be equal to n minus 1 complete loops, and then c minus L2 will be this distance. What we're trying to say is that L1 will definitely be equal to some number of complete loops, which is n minus 1 number of complete loops, and then c minus L2. So we do not really care about the number of loops that pointer will go. So there will be n minus 1, there will be some integer value of n and something, and the pointer will move those many number of loops. We don't really care about this. What we care about, that L1 will be equal to some number of loops plus c minus L2, and c minus L2 is the thing we care about, because c minus L2 is the distance between the meeting point and the starting point. So L1 will be equal to some number of complete loops plus c minus L2. So after completing n minus 1 loops, the pointer will reach c minus L2, and the total distance covered by that will be actually equal to L1, which is the total distance covered by the pointer from the start. So after n minus 1 loops and c minus L2, these two pointers will meet at the starting of the loop. So now that we have understood the logic behind the algorithm, let's try to code the algorithm. We'll first define two pointers, slow and fast. In the first step, these pointers will start from the first node, and we'll try to find the node where these two pointers meet, and that is going to be our meeting point. So as we said, our fast is going to move two steps at a time. So fast is being replaced with next of next, and slow is moving one step at a time. It is being replaced by the next node. And when the two nodes meet, when the two nodes become equal, so this is the condition which defines when these two pointers slow and fast meet. So this particular condition is going to handle the second case where we start one pointer from the start of the list and another pointer from the meeting point, and this condition is defining the meeting point. Now what we have done, we have defined another pointer travel, which is going to start from the head, or which is the start of the linked list. Now both slow and travel are going to move by one step. So slow is already at the meeting point, travel we have placed at the first node. Now both these move one step at a time, and we do this till the time they have not met each other. So when travel is not equal to slow, till that time we'll continue in this while loop. As soon as these become equal, we know that these nodes have actually met, and we come out of the while loop, and we simply know the point where they'll meet is definitely going to be the start of the loop. So in the end we have just returned slow, which is equal to the point where these two pointers have met, and as we discussed, this point is going to be the start of the cycle. Now let's talk about the time and space complexity for this problem. So the space complexity for this algorithm is big O of 1 definitely, because we haven't used any helper space. We are just using helper pointers, which is like constant space. So space complexity is big O of 1. Now the time complexity. So what are the total distances traveled by the pointers? Because the total number of iterations or operations is equal to the total distance traveled in step 1 and step 2. So in step 1, the total distance traveled is L1 plus L2, because these are the total number of iterations. So slow pointer is moving one step in every iteration, and slow pointer moves from start till the meeting point, and the distance from meeting point is L1 plus L2. So the total distance traveled, or the total number of iterations in step 1 is L1 plus L2. Now in the second part, what is the total number of iterations? So the slow pointer, or the pointer moving one step, will cover a distance of L1 again, because it moves from start to the starting of the cycle, which is a distance L1. So the total number of iterations are definitely going to be L1. So in all, the total number of iterations for both the step is going to be L1 plus L2 plus N1. Now now all of these L1, L2 and L1 again are less than N. Like L1 is less than N, L2 is less than N, because N is the total number of nodes in the linked list. So this total sum is definitely going to be less than 3N. So we can say that the time complexity is big O of L1 plus L2 plus L1. Or we can also say that the big O complexity is big O of 3n, which is equivalent to big O of n. So again, this problem also has a linear time complexity, which is same as our algorithm before, but we have actually reduced our space complexity from big O of n to big O of 1, as we are not using any helper space. So yeah, with this, I think we can end this video here. As always, if you have any doubts or any comments, do mention in the comment section, and I'll try to address them. And hope to see you in the next video. Till then, take care, keep learning. Bye bye.